For those who do not feel sufficiently familiar with the concept of virtual particles, we propose a small review of the phenomenon. In a field theory, the field, or rather the potential, is created by emitting a vector boson which has a certain probability of traveling to its destination. We will compute a small example coming from electromagnetic interaction. Consider an electron which enters with an energy E and a momentum vector p. It emits a photon with an energy k0 and a momentum vector k, and thus changes its energy to E' and its momentum to p'. The energy-momentum 4 vector must be the same before and after the emission of the photon, and in particular, the square of its length must be the same before and after. On the left, we get the mass of the electron squared, and on the right, the expression I'm writing down here. On the right, we obtain thus the mass of the electron squared, plus the mass of the photon squared, plus a mixed term. The mass of the electron cancels on the two sides, and the mass of the photon is 0. One obtains thus a relationship between outgoing energy and outgoing momentum, which is in conflict with reality because the energy becomes smaller or equal to the momentum. But the outgoing photon did not necessarily have a 0 mass. It can be a virtual photon, which has the mass squared that I'm now writing down. It is not equal to 0, indeed it can even be negative. It is clear that such a virtual particle cannot propagate in space and time. I just remind you that the Feynman diagrams are defined in energy-momentum space. Everything you see in a Feynman diagram happens at the same time and in the same place. So we must, of course, immediately reabsorb the virtual particle by another pair of real particles as shown in this diagram. There's a second current consisting of an electron which by entering and exiting a second vertex will absorb the photon.